here we go. So I'm going to try to keep this under 20 minutes. And we're going to kind of breeze through here. So if you need to pause the video, I suggest pausing it so you can look over your work. I did go over each problem, I double went over it to make sure that I didn't make any mistakes, but if you find one, you might find a mistake. I might catch it as I'm going through it too, but I'm hoping, because I had to rush through it a little bit, so we'll see. Alright, this one I know is right, and then, okay, so let me walk through it. Here, I did the chain rule. You could have FOILed it out. Either way you did it, you would have gotten this as your answer. So I did the chain rule, and then I had to FOIL these two binomials. I did distribute the two through. Over here I did the product rule. And after I FOILed, then all my dy over dx terms got moved to the left, and everything else got moved to the right, and then I divided. So this is your fraction. And then I plugged in the 0.11, and when I did that, you end up getting 0 over something. But 0 divided by anything is 0, so that's your slope. And then to write the equation of the tangent line, I put in the 1s, but really if you simplified, you just get y equals 1. So that should be the equation of the tangent line. Which means, in this scenario, that 1, 1 is a max or a min. Okay, and then number 2, you have to do the second derivative. So over here I have to do the product rule. Over here I don't have to do the product rule, but that's what you should have when you take the first swipe through the derivative. Then I move the dy over dx terms onto the left, and divided, and then I take the derivative of that. Well, the derivative of that is low d high minus high d low all over low squared, because you have to use the quotient rule, so that's what I did there. And then the dy over dx you have to replace. So dy over dx is this fraction here, so I took that, plugged it in. What was nice is when I did that, I had some stuff that canceled. And then to get my final answer, I just had 1 plus 1 gives me that 2, and then y plus y gives me that 2y all over the lowest squared. So that's pretty much as simplified as you're going to get. Okay, go ahead and flip. Okay, I did not simplify any of these for sake of making it easy for you to check, since there were quite a few problems in here. So that's your A and your B. I had to use the product rule for this one. So this is derivative of the first times the second, plus the first times the derivative of the second. This is e to the u times u prime. Down here, I have to do the a to the u rule. So this 3 is just outside, and you do ln of a, which is the base of the exponential function, and then times a to the u times u prime, and u is the exponent. Okay, and then number 4, you have to use log differentiation to differentiate it. So we take the ln of both sides, and this is what you would get if you simplified with the properties of logarithms as much as you could, because you'd break up that multiplication, and then the sin x is a power, so you can bring it out front, such as I did there. Then I went through and took the derivative, so this 1 over y dy over dx. The derivative of this would be ln of u, u prime, which that's u prime, over u, and then plus, I have to use the product rule here for that one. So that should be the product rule. So derivative the first times the second plus the first times the derivative of the second. So this is u prime over u for that second piece there. Okay, when you're ready, go ahead and flip. Okay, for number 5, I'd use the quotient rule here. So this is low d high minus high d low. And the d low is where you have to do the u prime over u, because that ln, all over low squared. And then for this one, you have to use the product rule. So this is the derivative of the first, which you have to use the log base a rule for that one. So it's u prime over ln of a times u times the second plus the first times the derivative of the second. Okay, now for number 6, I kind of had a typo here because, like, just so you know, on your test, you would not have that log base 3 there, because you would take the ln of both sides. Because putting log base 3 there made it a little bit crazy for you. But I did it with the log base 3 there. So first thing I did is I went through and broke up the argument as much as possible. So the top part is right there. That 3 was the exponent, so I could bring it out in front. Then you broke up the division by putting a minus. And then I broke up the bottom because they were being multiplied. So log base 3 of 5x cubed plus. And then I pulled that 1/4 out as the exponent, brought it to the front there. And then each one of these is that rule u prime over ln of a times u. So all of these are u primes, and then all of these are ln of a times u. So you can check your work. Okay, flip. Okay, for number 7, that's just knowing the rules for arcsecant, arctangent, and arccosine. It's u prime over the absolute value of u times the radical of u squared minus 1. You have to use the product rule here, so this is the derivative of the first times the second plus the first times the derivative of the second. The second one, you don't have to do any product or quotient rule here, you just have to know the rules. So this is u prime over u squared plus 1 plus u prime over the square root of 1 minus u squared. So again, you can check your work there to make sure you did it correct. Number 8 gives you those two expressions. First says to write theta as a function of x. So your first instinct, hopefully, was to write tangent of theta equals 5 over x. And then we have to write theta as a function of x, you have to take the arctan of both sides. And then I took the derivative of that. Notice I moved the x up to the top by making x to the negative 1. And then this is u prime over u squared plus 1. And then they told me that the speed of the plane is 400 miles per hour. Since it's flying this way, x is decreasing, making that value negative 400. And then I plugged in 10 for x. So I plugged in 10, multiplied by negative 400, I got 16 as my rate of change for the angle, my d theta over dt. And then I plugged in 3 and plugged in negative 400 to get that as my rate of change for the angle. Okay. Number 9. You set up this triangle. You know dx over dt is 3 because he's walking away, so it's increasing. Dy over dt then is what the tip of his shadow would be represented by, the moving of the tip of the shadow. And then we set up similar triangles. If you set up similar triangles and then get the y by itself, so I think I subtracted 6.5 and then divided 23x by whatever that number was, get that. And then I took the derivative of that to get this expression. I know dx over dt is 3, so I multiplied 3 and that together to get this value. And then, if this is dy over dt, and they want the length of his shadow changing, at what rate is the length of his shadow changing? The length of his shadow was y minus x. So now that I have dy over dt, I can take dy over dt and subtract dx over dt, which was 3. So that minus that gives me this expression. Hi. Sorry. Thursday. You have stuff in your box. I have them all on there. Yep. See if you can borrow one. Go talk to the librarian and see if she'll let you borrow one. Alright, And then this would be the next one for number 10. How you'd have to set it up. They tell you the diameter is 5x and the height is x. This is the volume formula for a cone. So I had to rewrite the radius as 2.5x because the diameter is 5x. So 2.5x got plugged in there. And the height was x. And then to get this decimal, I squared the 2.5, multiplied by pi, and then divided by 3. And then that's x cubed. And then I took the derivative, so brought the 3 out front, subtract 1 from the exponent. And then the instant that they're looking for is to find dx over dt when the pile is 10 feet high. So I plugged 10 in for x, and I plugged 12 in for dv over dt since that's the rate of change they gave me. And then I basically took 12 and divided it by that number to get that value at the very end. Okay. Thank you. I'll have him. Are you going to be around for a while?
Yeah, I got track.
Okay. All right. And then I tried to draw this picture, so I just decided to save me some time and you some time, and I'm going to zoom in a little bit. Okay. So this is the pool problem. To find the total volume of the pool, you'll notice that with this pool, you have a triangle. Like if I'm just looking at the pool, not the water, but just the pool. I have this triangle, and then I have this rectangle that's sitting on top of the triangle. Okay. So what they did is they took the dimensions of the pool, of the triangle part of the pool, and then they added the top, the rectangle, to get the total volume that could be, like if the water was filling the pool, how much water would be in there. Then they found the volume of 1 meter of water, which is in that similar, well, it says see similar triangle diagram, so they give you that expression there. Because you have this triangle, but only part of the triangle is filled with water. So they find that, and then percentage of the pool filled is the part, 18, divided by the total, 144, which will give you 12.5. Okay. Then for this one, V equals 1/2 BH. Hold on, I think I'm missing some direction here. Where's that 6 coming from? Oh, sorry. Yeah. They are giving you the volume for the rectangle part, I believe. 1/2 base times height times, yeah. Because the 6 is not changing. So that's why they're able to multiply by 6, because that's like the length of that triangle. So we have 1/2 base times height times 6. They replaced B with 6H to get 3BH. Or sorry, they already had 3BH and they replaced it with 6H to get 18H squared for your volume equation. And then they took the derivative of that and plugged in what they know. So 1/4 they knew was dH over dt. And then they're looking for the specific instance when h is 1, so they plug that in. And end up getting 1 over 144 meters per minute. Okay. Let's look at number 12. Okay, that one should be pretty straightforward. This one you have to This one you have to distribute through first, because when you do, you end up getting secant tangent, which the integral of that is secant, because the derivative of secant is secant tangent. And then for secant squared, the integral is tangent, because the derivative of tangent is secant squared. But you did have to distribute the secant through first. And then for C, you have to let u equal the exponent, and then find the derivative of u, then move the 16 over, rewrite it, so it's 1 over 16 times the integral of e to the u, and then the integral of e to the u is just e to the u. So that should be your expression there. Okay, so you're supposed to define integration. There's a bunch of stuff that we wrote in our notes talking about integration. So integration is the area underneath the curve. Integration is the accumulation of value. Integration is finding the original function. The difference between indefinite and definite. Indefinite is you have that plus c, which means it's just the family of functions. It's not a particular one, but like with your slope fields, it's one of them, but we don't know which one it is until that c is defined. The definite integral is having some boundaries and having a definite function that you're working with, so you know what c is, and plugging values in to find the actual area underneath the curve. So indefinite, we're not usually getting like one number answers. It's usually a function because it's representing the family of functions. And then for the definite integral problems, you're actually plugging numbers in to get the area underneath the curve or to get the accumulation of value. To integrate the function and find the differential equation, integrate the function can mean quite a few things. Find the differential equation usually means specifically that you're looking for the original function or for the general solution, which is like the family of functions. But depending on the problem, integrating the function could mean that, or it could mean find the accumulation of value, or it could mean find the area underneath the curve. But differential equation usually just focuses in on the original function. Okay, for number 14. That's your work that you should have set up. These are the x values that you should have plugged in. I got the 4/3 as the width for every rectangle because I took the amount of space I had, which was 8, and divided by 6 to get 4/3. And so to find these values, I just started with f of 0, because that's the first x value that I have to plug in. Then added 4/3 to that to get the next one. Then added 4/3 to get that to get the next one. Then added 4/3 to that to get the next one, so forth and so on. And I have 1, 2, 3, 4, 5, 6 rectangles in each parenthesis. So to find these values, I used my table feature on my calculator. I did not use the programs on my calculator, because this would be something like you'd have to show me that you'd have to do it by hand. So I'd want to see the y values that you punched out, and then adding all those together and multiplying by 4/3 would give you that. Same thing here, plug those in to find the y values, add all together to multiply by 4/3, gives you that, and then you have those three values once you find your lower, middle, and right sum. For number 15, explain the differences between the three types of Riemann sums, not only in terms of how they're set up, but also what the answers might mean in each case. So again, you just have to kind of explain how they're set up, what's different between the three setups. So like for midpoint, explain how you figure out what the middle value is for each partition. And then the answers might mean in each case. This one, the lower sum, usually means that you're missing some area because you're underneath the function. This one means most of your area that you're missing or that you have extra are canceling each other out. That's why this is the most accurate one. And then the right-hand Riemann sum is usually meaning you're having too much area. So when you draw in your rectangles, they're outside the curve more than they're inside the curve. So this represents extra area, not enough, and just right. But they are all estimates still. They're not exact. All right, go ahead and flip. For N3, the value that you should get there, and for both, actually. This one, there's no inside function, so you just have to distribute the 2 to the 1/2 through, and then integrate from there. And then we have to evaluate from 0 to 2, and if you do that, you get 1.508. Here, we're going to let u equal x plus 1, so du will equal dx, and then because I have that negative x on top, I have to rewrite for x. And then I come over here, so I replace x with u minus 1, and then u on both those parts in the bottom. And then I add those together, so I get u to 3/2, bring it up to the top, and then I distribute it through. Okay, so that's all simplification. And then I integrated this to get this, and then evaluated from -2 to 2, and I got -2.309. Okay. For number 17, there's some good pictures and words, like paragraphs that you can read through on those 2 pages to help you answer this question. But some of the key things that I'm looking for are you talking about how limits are involved with the fundamental theorem of calculus, and why the fundamental theorem of calculus finds the exact integral. You can use pictures to draw. There's lots of pictures of them showing how the limit will give you the exact value of the integral. So I'm not really looking just for a paragraph, but also for some pictures. And the best help I can give you is to look at those 2 pages and read through them and emulate some of those thoughts. Okay, last 2 pages and 4. Whoops. And I think for these, I'm just going to, for this I'm just going to show it to you because I think it's self-explanatory if you were to pause and look through it and compare it to your own. For B, this one you have to use the funky U substitution. So we're going to let U equal the bottom, du equals 2 dx, which then you have to move the 2 over because there's not a random 2 anywhere. And then I rewrite this one for x so that I can replace the expression on the top. So this next step here is rewriting in terms of u. So you can see I replaced the x up here with what it is in terms of u, squared it, -1 thought. Then I FOILed that out to get this, and brought the 1/2 up, and I just realized that I made an error. So that's going to be off quite a bit. Dang it. Scratch that. Okay. Because this should be 3/2 then. This should be 1/2, and this should be -1/2. Because I add the 1/4 and the -1 together. And I forgot to make that a negative when I brought it up. Okay, so when you integrate, you'll have the 1/2, and then adding 1 to the exponent here gives me 5/2. Flipping it gives me 1/20. No, 1/10. And 2x minus 1 to the 3/2. Adding 1 to the exponent here gives me 3/2. So if you flip it, you get 1/3. Adding 1 to the exponent here gives me 1/2. Flipping it gives me 3/2. And that should be the 2x minus 1 there. Yeah, so sorry so messy. I just realized I made a mistake, but that should be your answer there. Number 114 on page 307, because I ran out of room because I was writing too big. I'm just going to show it to you on here. Okay. That's the value those are the values that you should have for all 3. Zoom in a bit. And the work here is pretty self-explanatory, so I'm just going to let it sit there for a minute, and if you need to pause it to compare it with your answer, go ahead. And then we'll flip to the back page. Okay, on the back page, I didn't ask you to find the general solution, but I will ask you on the test tomorrow to find the general solution. So you have to integrate, move the x's, y to the y's, integrate, and then draw your slope field. Remember when you're plugging in these points that you're plugging it back into the derivative, not the general solution. And so those are my mini slopes, or the values. When I plugged in, like, let's say 1, I got a negative slope. For B, you're doing the same thing. This is the slope field for B. And then for 21, you have to find the general solution. So this is the general solution here. And then you have to plug in the 0.35, 3 for x, 5 for y, and solve. So I took this and I subtracted that to get this. And then that's my C value. So the last step there is just to rewrite in terms of C. Okay. And I think that's it. I will be here tomorrow before school. I can stay during lunch. I'll be here during 4th hour. Any of those times would be fine. And if something comes up or something doesn't make sense, feel free to send me a text tonight too, because I'll be around. All right, and that's it. This is Crisscross signing off.